Exercise 21C, signed area. The signed area is the area between the curve and the x-axis. So it's still an anti-differentiation, or antiderivative I should say, but you'll need to make sure that any parts that are under the graph, if I need to find an area, we mark them as being positive, and then we add all of the positive bits together. Because if you do, for example, if you were to just do a straight antiderivative, you might end up accidentally cancelling out some of the areas. We've got a variety of different formulas to remind ourselves on about antiderivatives, but let's just get started with some examples. So example 1, on a graph of y equals x squared minus 9, shade the region corresponding to this particular integrand there and calculate its value. So we want to find the area of this. So we're going to go and do the antiderivative. So we have found the antiderivative, and therefore the area is going to be 36 square units because we cannot have a negative antiderivative. Sometimes when we're doing this working out, if we want to get straight to the positive answer, one of the things that we do is we can put in absolute value lines. And absolute value lines look like these vertical lines here. And these vertical lines indicate that whatever the final answer is, it should always be the positive answer to this. It's a physics term. You sometimes might hear modulus being used. So the modulus of negative 36, or the absolute value of negative 36, is whatever the positive answer is. So sometimes you might see a vertical line being put there. That's just to remind you that that section there needs to be a positive answer at the very end. Example 2, find the area bounded by the x-axis and the curve for the following function. And so I've conveniently highlighted the sections here. So for these ones, what we can do is, much like in my previous example, we can put in a absolute value curves or lines for the sections that are underneath, just to remind us that those are supposed to be positive. Otherwise, alternatively, we can also go and do the old switcheroo. Now, why am I suggesting all this? Well, the reason I'm suggesting this is that if I was to do a straightforward so make that maximum 4 and make this minimum 3 and do all of this nonsense like so. What that will do is, as it's doing the antiderivative, it will be adding up all of the squares, but because this will be considered as negative and that will be considered as negative, it will just take this area and subtract that big area underneath there and that small area underneath from there, and therefore we'll get the incorrect answer. So what we do is we actually break it up into small sections. So what we'll do, if I label this, let's just call that let y equals f of x. This section will find just the antiderivative of that section, and this will be, now normally you would put the largest number at the top and the smallest number at the bottom. Well, actually, to be able to, essentially what we want to do is we want to get the inverse of that, don't we? We want to make sure that's a positive answer. So for that section, we can actually go and swap the terminals around, terminals being the limits, and that will get us a positive answer. And I'll put that as f of x dx. This section is already positive, so we can put 3 and 0, like so. And this section would be negative, so if we flip the terminals over, make that 3 and 4. And then what we'll do is we'll instead of doing this nonsense, we'll add all of this together. So we will do negative 3, 0 f of x. We'll add 3, 0 f of x dx. And we'll add the last one there as well, 3 to 4 f of x dx. So we're going to find antiderivatives from each of these. We'll have to expand this nonsense as well and find this out accordingly. So let's go. So there we have found the complete signed area underneath the curve, or in between the curve and the x-axis, which is this rather revolting 829 over 5. What I'm going to do now is I'm just going to show you, just using a CAS calculator, why we couldn't do the 4, -3 as I was suggesting. So in the CAS calculator, if you go into Math 2, you'll find the integration section. And it's this little button here that has the little integration symbol, and we want the one with the boxes on there, like so. So what we're going to do is just double check all of our answers, because even I'm not terribly sure. So let's go, well, actually before we do that, let's go and define our original function, shall we? Which was x times x plus 3 times x minus 3, x minus 4. Let's just go and make sure that works. Good. Just making sure that I expanded everything correctly. Yes, good. So what we're going to do now is do the antiderivative of each of those sections that I had suggested. So I can start with -3 and 0. And I got 567 over 5, good. And then we'll go 3 and then 0, 243 over 5, excellent. And then we'll go with 3 and 4, and got 19 over 5. So let's see what happens when we put 4 and then -3. And as you can see, we get an answer of -343 over 5. So it's not even the negative version of that 829 over 5, because what's happening when you do this, what it's doing is it's doing 243 over 5, take away 19 over 5, take away 567 over 5, and we get -343 over 5. So that's why we can't do the entire integration.